Hello everyone, thanks for watching this video. Today I'm going to talk about our work TinyLink 2, which is an integrated approach for developing IoT applications. I'm Boris Li from Zhejiang University and Alibaba Zhejiang University Joint Institute of Frontier Technologies. As we know, an IoT application generally contains three parts: the device side, the cloud side, and the mobile client side. Take the smart home as an example. The sensors and actuators belong to the device side. On the mobile client, there is a UI for users to view the data and control the devices. The cloud collects the data and generates commands for predefined rules. But developing an application that contains so many building blocks is not easy. For example, the developing language is complicated. As you can see, we usually use C or C++ to develop the device, Java to develop the UI, and Python or serverless computing on the cloud to achieve intelligent processing. Except for the various languages used in the development, this complicated cooperation slows down the development and makes the process error-prone. Hence, we are thinking about how to accelerate the development process. Let's look backward to see how existing works handle the complexity. For the device side, our last version, TinyLink 1, uses hardware-agnostic programming and automatic connection generation to speed up the development. For the mobile client side, there are many front-end frameworks such as Angular, React to simplify the development. And for the cloud, the FTDT, which stands for if this then that, provides an easy way for cloud-side development. We can see that the existing approaches only focus on rapid development for one side. The various language usage problems, complex interactions, and complicated data flow remain unsolved. So we need an integrated approach for all the three sides. This is what we have done. TinyLink 2 integrates the device side, cloud side, and mobile client side in one piece of code and generates the IoT application automatically. Before we dive into the technical details of TinyLink 2, we first introduce the usage of it. Developers only need to write the application logic using TinyLink 2 language in one piece of code. Then they need to feed the code to our system. Our system will generate the output for the three sides. The output of each side is then distributed to the corresponding hardware for execution. To be more specific, for the device side, developers could assemble the hardware devices with the configuration and burn the binary to it. The client program of the mobile device could be viewed through a pre-installed browser. For the cloud side, we build a rule engine to execute the policy defined in the configuration. This is how to build a complete IoT application with TinyLink 2. Building such an integrated development system faces non-trivial challenges. First, how to design the TinyLink 2 programming language to make it easy to use and expressive. Second, how to generate an IoT application with the best performance. We now talk about how TinyLink 2 cope with these two challenges. First, let's dive into the programming language design of TinyLink 2. We use a smart home scenario as an example. This application contains three smart curtains, which will open if the room is too dark during the daytime. Corresponding to the three sides of an application, there are three parts in TinyLink 2 language. Overall, TinyLink 2 adopts a C-like grammar, which is different from the traditional multi-language programming. The whole application is built based on the policy runs in the cloud. We call this approach cloud-centric. The policies are expressed with FTDT rules. On both devices and mobile clients, TinyLink 2 adopts the TinyApp model. A TinyApp defines the interfaces such as data and service and programs, such as the curtain on service. It could be called by the cloud or mobile device. If there are multiple devices designed for the same function, developers could simply instantiate multiple instances, such as SU1, SU2, and SU3. We also provide UI-related APIs for mobile application development, such as UI button and UI chart. In this code, we add a button B1 to open the curtain and chart C1 to show the light intensity read by SU1. Except for using the coherent language, this integrated development approach also facilitates users to explicitly define the interfaces and interactions without handling the detailed implementation. TinyLink 2 will generate the glue code for data flows and control flows. Nevertheless, based on the language design we stated just now, there are still some questions left unsolved. First, some of you may ask, TinyLink 2 adopts a cloud-centric development with FTDT rules. How expressive is the FTDT grammar? Second, the IoT application usually incorporates AI algorithm for prediction and data processing. How does TinyLink 2 simplify AI application development? For the expressiveness, we enhance the FTDT rules with new keywords to cope with controlling multiple devices or interfaces, such as all and for. Moreover, TinyLink 2 introduces a sensor query scheduling mechanism. Users could specify the deadline and miss ratio using the within keyword. TinyLink 2 will automatically generate the appropriate query interval that meets the requirements. For the second unsolved question, to simplify the AI development, we introduce the virtual sensor mechanism. Let us see through an example. Suppose I am a developer and I'm going to develop a smart door application. What I have are three sensors: a gyroscope, an accelerator, and a magnetometer. I have no idea of what AI algorithm to use and how to train a model. How could I build this application? With the virtual sensor mechanism of TinyLink 2, I only need to specify the relevant sensors of what I'm sensing as the input and define the output. TinyLink 2 will automatically select the best performed model and deploy a generate and record code to obtain the training data. In this smart door situation, the generate and record code will ask the developer to open and close the door back and forth. We just talked about how to develop an application with the TinyLink 2 language. Then we will talk about how TinyLink 2 optimizes the generated application. The optimizations include a static one and a dynamic one. The static optimization means this optimization is performed before the execution. During the code generation of TinyLink 2, we will detect the policies being executed at the cloud, which will damage the performance of the application. For example, the unreasonable deadline declaration in this piece of code. By domain language, suppose that transmitting the light readings to the cloud through Wi-Fi needs 100 milliseconds, but the deadline set by the developer is only 50 milliseconds. With static optimization, TinyLink 2 will shift the policy location to the device for better performance. If shifting the policy to the device still cannot meet the constraints, our system will throw a warning to the programmer. Another optimization is dynamic, which means this optimization occurs during the execution. The takeaway of this optimization is to automatically manage the data polling interval to achieve the best energy efficiency. How could TinyLink 2 do that? First, I will introduce the state-of-the-art approach to manage the data polling interval, which is RTFTDT. RTFTDT could dynamically adjust the polling interval to meet the deadline and miss ratio. This figure is a real-world experiment of RTFTDT with three sensors. We can see from this figure that Due to the tight coupling of sensing and uploading, the sensed data will immediately upload to the cloud. Even the two sensing events are very close. Is there an optimization space? Sure, there is. According to our preliminary experiments, we found that the network consumes most of the energy, while the sensor reading uses a little. So, to reduce the energy consumption without taking the risk of missing deadlines, we propose an early read and send optimization, especially for the devices with multiple sensors. As you can see on the slides, TinyLink 2 dynamically senses and uploads the PM 2.5 and humidity data earlier than the original schedule, and makes all the three sensors upload together. This optimization problem is formulated as mathematical equations, and we use a heuristic algorithm to solve it. You can refer to our paper for the detailed formulation and algorithm. According to our experiments, this dynamic optimization indeed reduces energy consumption. Up to now, we introduced the core building blocks of TinyLink 2, both language design and performance optimization. We implement the whole process of TinyLink 2 as shown in this figure. Then we conduct detailed experiments with this setting. We use 5 mainboards and over 20 peripherals as our IoT device, and we use a real-world cloud server from Alibaba Cloud and 2 smartphones as the mobile device. In this evaluation, we focus on answering these 3 questions. Question 1. Could TinyLink 2 accelerate the IoT development? Question 2. Could TinyLink 2 express the diverse IoT application logic? Question 3. Could TinyLink 2 reduce the energy consumption of the generated IoT application? First, to test the effectiveness of TinyLink 2, we conduct a user study to develop applications using TinyLink 2, IoT Studio from Alibaba Cloud, and Microsoft Azure IoT. The users include 6 PhD students, 8 master students, and 6 undergraduate students. The experiment contains 2 parts. The first part is to let users develop an application with a step-by-step user manual for each platform. Part 2 is to let users develop by themselves. Results show that using TinyLink 2 could accelerate the development process by at most 2.3 times than the industrial solutions. The right figure shows the comparison of length code compared to the native separated development. Data shows that TinyLink 2 reduces at most 94% of the length code. These 3 applications are all developed and deployed using TinyLink 2. Then we look further to the development process of TinyLink 2 and the industrial solutions to figure out how we reduce the development overhead. As you can see in this figure, with the industrial solutions, users first set up the platform and then develop the 3 sites separately. With TinyLink 2, developers could only write the code, upload the code, and deploy the output to the corresponding devices, which significantly reduces the development process. We now talk about the expressiveness of TinyLink 2 language. We randomly select 101 IoT projects and test whether they can be developed with TinyLink 2. We can see that, compared to TinyLink 1, TinyLink 2 could implement more projects. This is because of the addition of the cloud and the mobile side. There are still 15 projects that could not be implemented even with TinyLink 2. This is because they are built with handmade hardware or circuit, which are not supported in TinyLink 2 right now. Among the projects, the most used operations are actuator control and sensor data acquisition. The last evaluation I want to share with you is the optimization performance. As you can see in the last figure, the heuristic algorithm for solving the dynamic optimization problem in TinyLink 2 achieves near optimal NG performance compared with the other solving approaches. We also conduct a real-world experiment, and we can see that there is a 33% average NG reduction using TinyLink 2. Many other experiments evaluate TinyLink 2 in different ways. You can refer them from our paper. So to recap, TinyLink 2 is an integrated development approach for IoT applications on the device, mobile, and cloud side. We propose a coherent language that accelerates the development and tool optimizations for better energy efficiency. That's all from me about TinyLink 2, and thank you for your attention.